Hello, as introduced there, my name is Ian Muirhead and I'm from the Space Systems Engineering Research Group at the University of Manchester. Clearly the blurb I wrote a while ago saying I was going to do it didn't sound very interesting, but I hope it's a bit more interesting when I actually talk about what I'm doing. So I'm a postgraduate researcher at Manchester as a mature student, coming as a second career. And I'm lucky enough to be at Manchester under a teaching scholarship, so part of my time's on research, part of my time's on teaching, and I also moonlight at the Open University as an astrophysics associate lecturer as well. They're giving my first dip into education, so I always like to give something back. But what I'm going to talk about today is one of our undergraduate courses, the Space Systems module, and we did some work over the summer and over the last semester delivering it one lesson ahead of the students. In order to update and develop the modelling to increase their skills, and that's basically what I'm going to talk about today. So to talk about the course itself then, it's one of the compulsory modules on the undergraduate Bachelor's in Engineering and then the 4-year integrated Master's in Engineering. And on the left-hand side, you've got some of the first-year courses, which include the theory, which then lead into the module itself that I'm going to talk about in the middle of the Space Systems module. And it's a second-year undergraduate course, and then it leads on to some further courses in the third year. And from our point of view, or my point of view, one of the things that is really useful for it to lead on to is into the third-year conceptual aerospace systems design. So in the second year, it's an individual module, they're learning their own skills, and it's quite broad and shallow about space systems engineering. And then the third year is a group module where they will be allocated engineering roles as a electrical engineer, mechanical engineer, as part of an overall mission design. So they'll go much more deeper into their individual subsystem, but hopefully the second year will set them up with a broader awareness of the systems design and engineering problems across the whole spacecraft, and then they can start to work together better. So that's what I'm going to talk about today, some of the development we did in the space systems. And for information, the first half of the module is about the astrodynamics and the orbital mechanics mission analysis. And then they complete that by doing some GMAT coursework analysis, and that's worth 10% of the overall module mark, so quite a lot of work, so they only get 10%, but there's a lot of information, obviously, in orbital mechanics. But the bit I was concerned about and was involved in is the second half, which is through the space systems engineering, going through the main components of a spacecraft, the propulsion launch, thermoanalysis, doing some link budget analysis, make sure it's pointing the right way, and then making sure your power systems work, and also mass budgets are involved in that. And that was assessed by the submission of a report, MATLAB developed report, a bit of code in there, and that's worth 35% of the overall module mark. So between these two courseworks, you have 45%, there's 5% available for ongoing modules, and then the other 50% is then the final exam. So the coursework development in the MATLAB for the Space Systems Engineering is the bit that we worked on and we developed over the last summer. And learning objectives of the module, highlight some keywords there that are repeated. It's about the Space Systems Engineering, looking at the subsystems, understanding the development of the subsystem itself, making engineering decisions, looking at it as a whole overall picture. And that's the kind of thing we wanted to draw out of them and get the students to understand the bigger picture of what they're doing and to make decisions, because we've found students struggle to make decisions. They don't have the experience to say, you know, this is, I'm going to go down A rather than B. So they're the kind of skills that industry need to be able to make engineering decisions based on the evidence. So that's what we wanted to do. There we go. But it needed updating. So the first one was student feedback. They struggled with this part. It was a large amount of work for them, and particularly at the time of submission as well. There's a lot of stuff happening, and they felt quite smashed with it, so we wanted to try and refine it and make it a bit more coherent to them. You know, the students are never happy, but you can do whatever you can to try and make it better for them and get them more engaged. Go back one. There we go. I've jumped past my gifts. So the marking burden was quite spectacular, actually, I found, when we did it last year. So it was 35%. Effectively, they were submitting 4 reports. But the marking had become quite granular, where effectively you were marking out of 350 points for that 35%, and it was quite analytical. That takes a lot of time. It was quite coding heavy. It's hard to mark coding if you try to work out exactly the steps that somebody's done rather than their output. So that was killing the GTAs to do it and was taking quite a lot of time and effort to be able to do that. And actually the activities they were doing, they were covering all the subsystems in these 4 submitted reports, but they were quite separate. So they'd work on doing a launch and propulsion and then they'd go and do the next one, and the two weren't really connected. It wasn't a coherent mission as a whole. So part of the student feedback we got was that they couldn't see the overall big picture. It was, I work on this part of the spacecraft, and I give my answer, and then I work on a different problem, give an answer, but they're not one coherent mission, effectively, which is something we wanted to develop. There we go. And then susceptible to AI. So this is something that we talked about in this workshop last year, actually, about the impact of AI on education and engineering. And if anybody was here last year, we all stood in a line and said between 1 and 10, if you were at a 1, you were terrified of AI and you wanted everybody to have a pen and paper and in a classroom when they're doing an exam, or if at 10 you were embracing AI. Well, I was about an 8 or a 9. I'm really keen on AI, and I think we should try and integrate it in our work while protecting the academic integrity of our work. So it was to try and bring in AI as a response to that. So the first thing we did then was agree to do lots of things and then waste loads of time doing other things, so we had to catch up. But in the summer we had an undergraduate intern who came in, and this student was really good, had completed the course in the previous year and spent the summer working on how to develop and update the coursework based on their own experiences and some top-level guidance they were given. And they focused on making a single mission design thread, so it was a mission that they could then connect each different tutorial into an overall single spacecraft. And based on their own experiences, the key skills that they felt they lacked at the end, then looking forward to their third year, and also how the explanation was delivered. So what did they struggle with as a student in trying to do the coding, trying to do the analysis? How did they, what problems did they have? So maybe we could framework that a bit better so they could focus on actually the overall objectives rather than worrying about a bit of coding. And then we told them to include AI and to test it. And in fact, tried to get AI to answer any of the questions that we're doing using the open source, ChatGPT, all that kind of good stuff. And he did some really good work. Obviously, it wasn't perfect. It wasn't the final product, so it took then we could take that and build on. But it was a really good foundation to look at. And effectively, it was a singular mission that was updated. So it was for this a next version of a Sentinel satellite was the core mission, and we used Sentinel 6A, the previous satellite, as the baseline standards for all our parameters. And then they could build on that and develop it for a new mission with slightly developed objectives and requirements. And the output was a series of 5 tutorials, and each one allowed them to do some analysis, do some modelling and coding, get an output, and then make an engineering decision off the back of it. So the first one was a launch propulsion sensitivity and mission analysis. So that sensitivity, they worked out what thrust they required in order to achieve the mission objectives, how much fuel it needs, and then made a decision. And the output was that how much mass they had to launch with on the spacecraft. And then there were some further elements about launch site selection, so they were applying the orbital mechanics parts they'd learned. They went on to thermal design, where they, based on the parameters they were given, they had to model the spacecraft, and if they did it right, they'd realise that it would quite quickly freeze and stop working. So then they had to make a decision on how they were going to fix that, and they had a number of options that was completely down to them. They could look at changing the materials, they could look at adding components, heaters, and if they could find a novel solution that I hadn't thought of, they could go away and do that as well. There was no restrictions on what their answer was, and there was no expectation for them to find our solution. And the knock-on impacts was then maybe they'd need power, additional power requirements. So it was building up a picture of the spacecraft that was actually unique to their engineering decisions. It went on again, communications link budgets. They'd choose based on the analysis what equipment they'd use, impacts there on power, impacts on mass. And then again, modelling attitude determination, and then finally coming to the power and mass budget. They'd add everything together, look at, okay, what does that mean for my power? How big's my battery got to be? How big's my solar panels got to be? And then finally, what's the mass of the spacecraft? So they've put together a singular, coherent picture of the spacecraft based on their own decisions, and every student could have picked a different path to answer that question, and they had to make decisions along the way. And I actually didn't care what their decisions were, as long as they thought about it and justified it. If it was a reasonable answer, we'd say you've done a good job. And that was a bit more reflective of a real mission design, and added different skills and made it a coherent whole. And the first one, they did the first one, and it was formative. They didn't get assessed on it, and then when they'd finished and worked on it, at the end of the week, they got a lovely video of me saying, and here's one I prepared earlier, and I taught them through it, and I gave them an example, so they weren't flying blind. And then the 4 summative assessments, and the formative one were then put together, and they submitted a single report. So as markers, we had 1 report to mark rather than the 4 separate ones, which was good. AI use was permitted. So the way we designed all the questions and updated all the questions, there was no what's this? If we give you X, the answer is Y, which AI can answer really well. A lot of this was subjective decisions, which AI doesn't answer very well. So we removed all the questions that we thought were susceptible and became very much a decision making. But they could use AI, particularly for the coding, because AI is really good at coding. So let them do it, because that's probably what they're going to be doing as soon as they've left university. So they were allowed to use AI in the coding. And this is where it comes to the marking. So rather than a pretty difficult, quite granular analytic marking, we got a bit more holistic, where you judge the standards and the output of what they'd done against pretty simple criteria, not quite done. You know, if they didn't bother, they didn't get any points. But if they did it and it didn't work, they still got some points for unreasonable effort. If they achieved the goals but missed some elements, they'd get it done, and then they'd get well done if they met great standards. But it's not very detailed, so if it met the standards as judged, then you could have quite a range of decisions and still get good marks. And also the weighting we did for it, effectively the 4 that were submitted were worth 25% of the overall coursework element, and 10% for the structure and explanation in the MATLAB live script. AI doesn't write that, so you know that's very much an individual's writing. Only 5% was on the coding, and actually if you used AI to do all your coding, you'd probably at best get just done. So out of the 25 marks available for each of the element, you'd only get 3 if you got AI to do it, because AI can't do the rest of it very well. So we reduced the weighting of the coding and just made it less important in the overall output. And then finally the discussion. So again, the questions, why did you do this? Explain your decisions based on your evidence. AI doesn't do that very well, and that was worth 10%. So it moved away from the worry about AI just doing everything. And most importantly, it was far easier to mark, because you can make a holistic judgment of, yeah, the students achieved the goals, they've justified their answers, they're graded in this way. So that went really well and made the marking a lot faster. And the students were quite happy with it. They still complained that it was a massive burden of work at the same time as other stuff happening, but hopefully it was a bit less, and it was a bit more coherent, because over the course of the second half of the module, they built up this report and they had the structure of where they were going, and they could just build on it each week, so they didn't have to just write the whole thing at the end. Some did, of course. The standards of what we got, I thought were quite good. It was improved this year, I think, with all the structure and framework, and we'd focused on areas where they were struggling with previously. I think the standards were improved. The marking was much easier, and we didn't really have any AI plagiarism issues. There was nothing standing out that it looked like they tried to use AI to write anything, or if somebody did, it just looked rubbish and they didn't get a good score. So it was a reasonable, I think, response to the stresses of AI in education. And where we want to go to it, because like everything, we were trying to develop it and then trying to deliver it, and life, the universe, and everything got in the way. I don't think we probably quantified the effects of it as well as we could, and I think there's possibly a bit of work to look at how the previous grades and the grades of the students that took it last year, and how it's developed and improved or changed their outcomes, and also the reflection on their submissions and the questionnaires they complete at the end. And also it'll be good to see what the third year follow-on is. So the group that did this tutorial in the last academic year, and then this coming academic year, will now do the third year design project. And we're hoping some of the challenges that they faced in understanding the bigger picture, in putting it together into a coherent mission, will be reduced. And they've actually got a framework of modelling that they can use and adapt. And I think potentially there's like a scholarship of teaching and learning project in there, if we have time and the ability to do it, to say how we developed this, and particularly the AI stuff, how we responded to AI and included it in our work. Well, I think there's a continuing review of realism. You want to make sure it's up to date, it's current, a bit of development, and make sure all our numbers follow through correctly, so they're not making something that's totally unrealistic in the spacecraft. And we'd actually like to increase the overall weighting of this particular module, this particular part of the module. So rather than it only being worth 35%, increase it, because the burden of work is actually quite large, and they're getting a lot out of it, and it's testing skills. So maybe we can reduce the weighting of some of the other elements of the module and increase it here. Again, making it a bit more open source. MATLAB is a licensed, paid-for activity, so potentially using Python and Jupyter notebooks, which are free and open source, or giving them the option one way or the other. Again, that comes with challenges and marking burdens. And something I'd like to consider doing is to explicitly integrate AI. So rather than saying you can use AI to help you with your code if you wish, developing some part of it that says use AI and go away and do it. Because I certainly feel that that's what a lot of engineers will be doing as part of their framework in the future. It will be a tool that everybody will apply. So that was basically what we did. I think it went quite well. The students seemed more happy. I hope they're better prepared for next year. And it was enjoyable trying to write it. I hope it's got good skills. And that's my presentation. Thank you very much.